In this video, we have just a single objective. Find side lengths of special right triangles. Now, before we launch into the specific details of that, I'd like to examine things that we've already done. Here's a right triangle. Figure out the side lengths. So using trigonometry, what would we have to do to figure out the lengths of these sides, x and y? Well, we've already seen before that based on the 45-degree angle, x is the opposite side length, 4 is the hypotenuse. Based on opposite and hypotenuse, we know that is sine. So we have sine of 45 degrees equals opposite over hypotenuse. Based on trig, we've seen before how to build equations. Of course, we've also seen then what we would need to do to solve them. So simply typing these into our calculators, x multiplied by the sine of 45 degrees gives us, and our calculator gives us 2.8284 blah blah blah, and it keeps going. And typically we've rounded these to the nearest tenth, to the nearest one decimal place, telling us x is equal to 2.8. Okay, fine. We have an approximate answer, a rounded answer. Let's now determine the value of y. Well, based on that 45-degree angle, y is the adjacent. And so we could build cosine of 45 degrees equals adjacent over hypotenuse. And this is going to give us the exact same answer. I'm able to recognize that pretty quickly because remember what the cofunction theorem tells us? The cofunction theorem told us that sine can be turned into cosine by doing what? By taking the complementary angle. The other angle in the triangle. Well, what is the other angle in this triangle? 45. It's a 45 degrees. And so what we're noting, here's a fact that I know very well and that I hope that you'll figure it out before too long as well and just internalize it. Sine of 45 degrees is the same thing as cosine of 40 degrees. So this piece that I built in the red is the exact same equation as what we had in the blue originally. That's why I was able to get my answer so rapidly and simply say it's going to be 2.8. Approximately, or rounded. Let's do the same thing with this triangle. Find the values. For this one, we're basing it on the 30-degree angle. And so to figure out the value of u, I'm recognizing that u is the hypotenuse. 2 is opposite. And so we can build our equation. Sine of 30 degrees equals opposite over hypotenuse. And we've seen what we need to do to solve it. This particular one, we actually saw that there are 5 different ways to solve it, and so one of the most popular ones we had was to simply create the proportion cross multiply. U times the sine of 30 degrees equals 2. And then dividing to cancel out that multiplication led us to u equals 2 divided by the sine of 30 degrees, which isn't a big deal. We can type it into our calculator. And it turns out to be a perfect 4. Not a rounded 4, a perfect 4. And I know I'm rushing through these fairly quickly because, of course, we spent a bunch of time on it. This is just a quick review of things that we already know. Similarly, we saw that we could set up cosine of 30 degrees equals adjacent over hypotenuse. But now that I know that the hypotenuse is 4, I'm going to use it. And so we'd get multiplying by 4, v equals 4 times the cosine of 30 degrees. And after we put that into our calculator, we get 3.46 blah, blah, blah. So we rounded it to 3.5. The point is, behind these problems, these two problems are actually examples of special right triangles. When we have a 30-degree angle, of course, its complement is going to be 60 degrees. A 30, 60, 90 triangle is considered special. Likewise, a 45, 45, 90 is considered special. Now, I want to emphasize why we're going over these pieces, because why would we want to have a different way of doing it when we just demonstrated we already have ways of figuring out the side lengths? We already have answers. Well, a couple of things worth noting. With our study of trigonometry so far, we've focused only on right triangles. Trigonometry also requires us to study circles. And these pieces that we're going to do today with special right triangles, for everything that we are doing in geometry, we will not need the information. We already have a way of just getting answers. Nevertheless, the pieces that we're doing today, you need to still learn, because when you start doing some basic circle trigonometry in Algebra 2 and in pre-calculus, circle trigonometry is absolutely a huge part of it. It's actually 2 whole chapters in pre-calculus, so it plays a much larger role there. And I'll just let you know, if you don't have these special right triangles down, when you try doing circle trigonometry, it's going to be way, way more difficult for you. I remember a couple of years ago, I told Scotty that he had to have this stuff that we're doing today completely and totally memorized for trig, and he didn't believe me. And so he struggled constantly throughout the entire trigonometry class, because this stuff that we're doing serves as a fundamental building block to make circle trigonometry easier. It's used constantly there, all the time. And so you have to have it there. You can get away with not knowing it yet. But it's still going to be nice, because what we are going to notice with these special right triangles, they will still give us, in geometry, shortcuts. In particular, we saw that we can get answers for 30, 60, 90. We can get our answers for side lengths on the 45, 45, 90. The relationships we're doing in this video are shortcuts that make it faster and easier. So let's go with them. First things first, we'll build the 45, 45, 90 degree angle. Also note that, of course, this piece was the hypotenuse. And going back to my last example, I'd like you to tell me, what did you notice about the legs? What happened with the legs in our example that we did before? 2.8 and 2.8, they're the same. When we have a 45, 45, 90, one of the important things that we can note, the legs are the exact same length. Coming over to the 30, 60, 90, we have our 30-degree angle, our 60-degree angle, we have the hypotenuse, we have a 90 degree. When we reference the sides, we will reference the short leg and we'll reference the long leg. Do you remember how when we created the definition for sine, cosine, and tangent, that a lot of our problems were based on, okay, you look at the problem, recognize which piece of sine, cosine, or tangent you had, and then you just plug them into the equations and solved? We're doing the same process here. With the special right triangles, I'm going to give you some notes or some equations. You will look at the picture, recognize which pieces were given, short leg, long leg, hypotenuse, recognize which piece we have, and then it's just putting stuff into the formulas and solving. All right, so continuing, putting down the same information. Please notice we have 45 degrees, 90 degrees. The hypotenuse and the legs are the same, so here's the most important part that you have to have written down. This is the stuff that I'm putting down in the black right now. This is what you need to use throughout all of our topic. In a 45, 45, 90 triangle, there are two facts. The first, the legs are the same length, so leg equals leg. The other fact, if you take one of the legs and multiply it by the square root of 2, it will give you the hypotenuse. That's what you need. The square root of 2 is approximately 1.414. But it's not a perfect, smooth, even number. It's not a fraction or anything. Its radical form is just the square root of 2. Now, where this piece comes from, let's just make up a number. Let's say that my leg is 1. So that means the other leg is 1. And based on the Pythagorean theorem, legs squared plus legs squared equals hypotenuse squared. So 1 plus 1 equals hypotenuse squared, 2 equals the hypotenuse squared, and simply taking the square root, you see where the square root of 2 comes from? It's just because of Pythagorean theorem. Well, with a 30, 60, 90, we'll have similar notes. In a 30, 60, 90 triangle, we had hypotenuse, 30 degrees, 60 degrees. We had the short leg, and we had the long leg. Once again, there will be two equations, two relationships. This one gives us the short leg doubled will equal the hypotenuse. The other relationship, if you take the short leg and multiply by the square root of 3, it will give you the long leg. This stuff in the black is what we need. Thus, for every problem we do, we will use one of these 4 equations to help us out. And we'll start with this first example. Now, I would like to point out an option already. You notice the problem we started with earlier? And the problem we're doing now? It's the same thing. But please notice the directions are different. These directions tell us, leave your answer in simplest radical form. Simplest radical form means absolutely no decimals. It also means absolutely no rounding. Based on these directions, if you did this stuff that we did before, you're not going to get credit because it's not checking the skills that the directions are asking us to do. All right, so let's start here. What type of triangle is this? Is it a 45, 45, 90, or is it a 30, 60, 90?
45.
Okay, because it's a 45, 45, 90, we know two facts. Leg equals leg, and we also know leg multiplied by the square root of 2 will equal the hypotenuse. Well, here's what we need to do then. if leg equals leg, we know that x and y are actually going to be the same number. So we don't need to do two different things, we just need to get one of them. Well, what pieces do we have then?
Okay, square root 4.
We know 4 is the hypotenuse, so 4 will go in the position of the hypotenuse. We also know x is the leg, so we have x multiplied by the square root of 2 equals 4. The geometry now is done. We just have to solve it and simplify it. So what do we have to do to get the x by itself?
Times 2.
Okay, because we have multiplication, one thing we can do is divide. And so we have divide by the square root of 2, which cancels, telling us x equals 4 divided by the square root of 2, which is a correct answer. If you took 4 divided by the square root of 2 and put it into your calculator, it's going to give us the 2.828 that we had before. But this is not simplest radical form. Simplest radical form does not allow square roots in the denominator. So how do we get rid of a square root in the bottom? The process we need to use is called rationalizing the denominator. You'll probably remember from your earlier classes that a square root times a square root is the number itself. So that's what we'll do. If we multiply square root times square root, those two things will cancel out and there won't be any roots in the bottom. Of course, since we multiplied the denominator, we have to multiply the numerator the same way. So that gives us 4 times the square root of 2 over root times root, the number itself. And we can then observe that 4 over 2 simplifies. And so this becomes 2 times the square root of 2, and that's the simplest radical form. You'll notice this one was the example we did before also. Fortunately, this one is going to be a little easier. What type of triangle is it? 45, 45, 90 or 30, 60, 90? Okay. As a 30, 60, 90, we know that the short leg multiplied by 2 will give you the hypotenuse. We also know the short leg multiplied by the square root of 3 will give you the long leg. Those are the two relationships we need to use. So which side do we have to start with? What is this 2? Is it short leg, long leg, or hypotenuse? As the short leg, we'll just plug it in. Short times 2 equals hypotenuse. How big is the hypotenuse? 2 times 2 is 4. Done. We've got the hypotenuse. Let's now go get the long leg. The short leg multiplied by the square root of 3 equals the long leg. Oh, sweet. That's already in simplest radical form. We're done. We have the hypotenuse, we have the long leg, we have the short leg. And please notice how little work there was compared to what we had to do before. A lot less work. This is the primary advantage to working with special right triangles. Whether you have a 45, 45, 90, or if you have a 30, 60, 90, once you get used to working with these equations, you can figure out side lengths very, very rapidly, as in 1 or 2 seconds is all it'll take. What type of equation is it, or triangle is it? 30, 60, 90. So we would have the short leg times 2 will give us the hypotenuse. We also have the short leg times the square root of 3 equals the long leg. Which piece are we given? Is this piece 5 times the square root of 3? Is it the short leg, the long leg, or the hypotenuse? Since it's the long leg, we'll put it in its position and then check. The short leg multiplied by the square root of 3 equals 5 times the square root of 3. How big is the short leg? Well, what would you do to get the s by itself? Well, one way to do it is to recognize division will cancel out multiplication. So the short leg is equal to, well, square root of 3 divided by square root of 3. Number divided by itself. That's 1, so it cancels out, and we have the short leg is equal to 5. Sweet. Y is 5. Now let's get the hypotenuse. Knowing that the hypotenuse is, or the short leg is 2, 5 times 2 equals x. Sweet, that's 10, and we're done. Here's a similar problem. What are the relationships here? It's a 45, 45, 90, which tells us leg equals leg. So U and V are actually the same thing. We also know that the leg multiplied by the square root of 2 will equal the hypotenuse. So leg times square root of 2 equals hypotenuse. What's the value of U? Noting what this is telling us, the leg attaching a square root of 2 equals hypotenuse. Well, basically, if we just unattach or detach the square root of 2 on both sides, that's pretty easy. U is equal to 8. And V is equal to 8. We're done. So what type of triangle? 30, 60, 90, which tells us what equations? Short times the square times 2 will equal the hypotenuse, and short times the square root of 3 will equal the long. So which piece are we given? This number 3. It's the hypotenuse. So we would have the short leg, which is B. So we'd have short multiplied by 2 equals hypotenuse. What is the value of your short leg then?
1.5.
When we divide by 2, we'd get B is equal to 3 over 2, and Josh pointed out that this is the number 1.5, which is correct. Radical form, though, does not use decimals. So I don't want to have a decimal here at all. I'm just going to leave it as an improper fraction, 3 over 2. And then we'll progress. The short leg multiplied by the square root of 3 equals the long leg. Basically, short leg, you attach a square root of 3 with multiplication. Sweet. That's our long leg. We're done. You'll notice when we attached that square root of 3 through multiplication, the multiplication tells us to put it in the numerator. So we have a 45, 45, 90, which tells us leg equals leg. So square root of 3 times the square root of 2 equals y. Leg equals leg. Awesome, got that one instantly. We also know that a leg multiplied by the square root of 2 will equal the hypotenuse. So a leg multiplied by the square root of 2 equals the hypotenuse. Well, how do we handle this one then? A root multiplied by a root is the thing itself. So that's just 2, and keep the 3. 3 times 2 equals 6. We have our answer that quickly. Compare how fast it is to get some of these side lengths and some of these answers with what we had originally. We already know we can get the answers. Using trigonometry, we can always figure out side lengths. We can always figure out, with inverses, we can figure out the angles. Those are things that we already know. But this just gives us another way to get the answer with some triangles. Only with these special triangles. But it does make things quicker and easier for us. Thus, we finish our video for today. We've seen that we can use the side lengths of special right triangles, or rather we can use the relationships of special right triangles to figure out side lengths.